All right, so somewhere on Canvas, I've attached this file as a PDF. These are my Lewis structure guidelines file. So these are the steps that I go through and what I would recommend that you go through to find the best Lewis structures. You can use this as kind of training wheel. So in the beginning, you're going to have to refer to this a lot, but as you do more and more practice, you'll eventually not need it. Right. So our first step is to count valence electrons. Remember to not forget about the charges. So for example, this is a 2 minus, so we add extra 2 electrons. This is a +1, so we subtract 1 electron away. The next step is probably the most difficult one, and that's to draw the Lewis structure correctly. Remember that H is always terminal because it can only form one bond. So in this case, C2H6, we draw the 2 carbons in the middle and then the H's surrounding them. Remember that the less electronegative atom goes in the center. So for this negative OCN, it's the carbon, because it's the less electronegative, that goes in the center. Yes, I also wrote it out as OCN because that is the correct way to write out the formula, but you can write ONC and you should still end up with this Lewis structure. Another one that really tricks people up is N2O. A lot of people want to put the oxygen in the middle because, it's like kind of the odd one out and there's 2 nitrogens, so it kind of makes sense. But nitrogen is actually the less electronegative atom, and so it's what goes in the center. So one of the nitrogen goes in the center, and then another nitrogen and oxygen go on either side. So be careful of that one. I like to use that one to trick people up. Remember that OH is a common motif, especially in acids, which we'll learn about in a little bit. So there's for HNO3, put the nitrogen in the middle, surround it by oxygens, and then make an OH because it's a common motif. Again, this is probably the hardest step and the one that relies on experience the most. Sometimes the formula gives you a hint, right? So CH3, that tells you that there's 2 CH3s on either end, and then there's an oxygen in the middle, oxygen in the middle. After that, the steps kind of get pretty formulaic and it's really not too bad. After that, we add bonds, then lone pairs. Remember to keep count of electrons available. So we start with 1 bond from each terminal atom to a more central atom. So there's our, we added those bonds and that used up 4 valence electrons. We're left with 12. And then after that, you give atoms octets, starting with the most electronegative or terminal atoms. So for example, we had 18 valence electrons here. We put these single bonds. That got us down to 14 valence electrons. How do we split them up? Well, they're all oxygens, so they all have the same electronegativity. However, these oxygens are terminal. This one's more central. So the outer ones get a filled valence shell, and then we actually run out of electrons to give this one. So it gets an incomplete octet. Later on, when we add double triple bonds, that'll get fixed. Right after that, then we want to move lone pairs to form double and triple bonds to A, fill octets, which is the most important thing, and then B, to lower formal charge, which is also important, but if you have to pick one or the other, pick filled octets. So there's our example of, taking a lone pair from each oxygen to form our carbon dioxide structure, and then boom, everything has a failed octet. In this case, it also has all formal charges of 0, which is why we grab one from each oxygen. If you try to grab 2 lone pairs from the same oxygens, you'll end up with formal charges. Remember that period 2 cannot have more than an octet. So even though we have formal charges here, you might be tempted to draw another double bond. You're not allowed to do that because nitrogen is a period 2 element, and so it cannot have more than an octet. So you want to stop it here. It does have a resonance structure, though. Remember, hydrogen only wants 1 bond or a duet. Beryllium only wants 4 valence electrons or 2 bonds. Boron and aluminum only want 6 valence electrons or 3 bonds. Period 3 and below can have more than an octet if it minimizes formal charge. Remember for sulfuric acid, we broke the octet rule because it helped minimize formal charge. So to create double and triple bonds, another purpose, if everything already has an octet, the other purpose is to minimize formal charge. So there's the equation for formal charge, right? And you can see an example problem there. The lower the formal charge, the better, right? So there's our CO2 where we took lone pairs from 1 oxygen. You see we end up with formal charges, whereas if we grab a lone pair from each oxygen, then we end up with no formal charges. If you do need a negative charge, give it to the more electronegative atom. So we see in both of these structures, we have a formal charge of -1. On the left one, the negative is on the oxygen. On the right one, it's on the nitrogen. Since oxygen is more electronegative, the left structure is better than the right. And then finally, if you made an arbitrary decision, then there are other resonance structures available, right? So here's our structure of carbonate. or a step in the structure of carbonate. And in this step, right, our carbon does not have a filled octet yet. So we want to go ahead and make one of the lone pairs into a double bond. But we could pick any of these three oxygens, right? There's no reason to pick one or the other. So you're making an arbitrary decision, which means in real life, you're going to have a combination of all of these, right? So then you draw out all of these resonance structures. You fill in the formal charges. You note that they're all equally good. And so your real structure is a combination of the three with the bond order 1 and 1/3. Again, practice. If you find this thing helpful, go ahead and use it as a training wheels, but obviously you want to get away from it eventually. Or if you find another online resource that works for you, that's totally fine too. The objective is to be able to do it.